Okay, here in section 8.5, we're going to take a little break from the theme so far of chapter 8, and that was these advanced integration techniques we were looking at, and we're going to look back at something we've seen before, what are called indeterminate forms, and then a new technique for maybe dealing with those indeterminate forms called L'Hopital's rule. Ultimately, this whole section is revolved, or is going to be involved with the topic of taking limits. So certainly not this integral topic we've been seeing so far, but a more advanced way of looking at limits. Okay, so just a one slide quick review of what we've seen so far concerning limits. The first thing I hope you remember way back from chapter 1 is we always use direct substitution first when evaluating a limit. In other words, we just take the value that x is approaching and plug it in. If we do that in a very basic problem, which we really never saw in this class, of course here we would get 3 squared plus 1, which is 10, and if it turns out to be a nice easy number after you plug in the value that the limit is approaching, then that's the final answer. Problems at infinity, or as the limit goes to infinity. As a reminder, in case you need this reminder, that was back from chapter 3, specifically section 5. Basically, other than chapter 1, this is the only other time we've seen limits. But either way, here we have a limit going as x goes to infinity of this particular rational function. And if you remember, there was 3 steps in figuring out what this limit would be equal to. The first step was to ignore the things in the top and the bottom that really don't matter. And the way you made that determination was by the lower power things. Those kind of just get crossed out, and then we're left with whatever we have in the top and the bottom. The second step was to then simplify that expression. We have an x squared in the bottom, we have 3 x's in the top, so of course 2 of those can cancel in the bottom with 2 in the top. And we're left with negative x over 10. And then the last step is to evaluate the limit. If we plug in infinity, negative infinity over 10 would of course just be negative infinity. And also as a follow-up, remember this had to do with this concept of finding horizontal asymptotes, but not really important concerning what we're talking about here in 8.5. Those what I would call basic ones in a sense. The ones that I think for a lot of us that give us more of a headache were the ones that produced, or limits that produced, something called an indeterminate form, which is just a mathematically meaningless expression. And then the 2 we saw, especially back in chapter 1, which was 0 over 0, and what we saw in 3.5, but we had ways of dealing with it, so it wasn't really too bad, was the infinity over infinity version of an indeterminate form. Bottom line is, if you were to ever see these 2 types of forms, that would just tell you to do more work. And the more work that you saw back in chapter 1 was to do some sort of factoring and canceling. So here's just a nice little overview of the types of limits we've had up until now. 0 over 0, which needed more work. The limit needed more work. If we got 0 over something that's not 0, that limit was 0. And of course, if we got something that wasn't 0 divided by 0, that was an infinite limit, and that required a different technique, but we're not going to focus on any of those types for the purpose of this lesson. So just as a nice little review of an indeterminate form kind of problem, if you were asked to take this limit of this rational expression as x approaches 3, you should of course resort to the direct substitution first, and then you would have saw we got 0 over 0, which doesn't mean anything, indeterminate form, which tells you to do more work. Really the only technique we studied in this class in terms of doing more work was this factor and cancel technique. We needed to factor either the top and or the bottom, cancel whatever we could cancel, and then we would take the limit of that new expression. And as it turns out, in the top of the fraction we can factor out a 2, and then we're left with a difference of squares. X squared minus 9 becomes x plus 3 times x minus 3, and then luckily this worked out nicely where those x minus 3's would cancel, and really we're trying to take the limit of 2 times x plus 3. That was kind of the whole point of this whole needing to do more work. making this original limit, which didn't work out, into a limit that would work out. Now we can retake this limit, of course, by plugging in the value of 3. 3 plus 3 is 6 times 2 is 12. Okay, so then why do we need to relook at limits, and what is this whole thing called L'Hopital's rule? Well, the reason we need to revisit limits, for definitely several reasons, especially for some things that are going to come up here at the end of Chapter 8 and certainly in Chapter 9. The reason we need to revisit these limits, other than that reason, is what about limits that we couldn't do? What if we couldn't do a factor and cancel so that we could take a limit if it was an indeterminate form? Well, luckily there's this little thing called L'Hopital's rule, and it's given right here by what you see boxed in red. If you ever have the limit of one function over another function, that can actually be rewritten, if it's helpful, as the limit of the derivative of that top function divided by the derivative of the bottom function. And please make a note, it's probably the only error I've really ever seen here, but this is not talking about using a quotient rule. Remember, the quotient rule had that whole low D high minus high D low over low low. This is not a quotient rule. All we're doing is taking a limit, and within that limit, taking the derivative of that top function separate from the bottom function, which certainly was not how we do derivatives when we're taking a derivative using the quotient rule. So just be very careful you don't confuse that for some sort of quotient rule, because that's not what we're doing here. So that's essentially it. L'Hopital's rule says that if the top and the bottom are differentiable functions, then the limit of the function is equal to the limit of the derivative of the numerator divided by the derivative of the denominator. So a fairly easy concept, and especially you'll see this when we start practicing it. Just a little bit of quick background about this person that it's named after. It actually turns out he's not really the one who discovered it. If you kind of read this little excerpt here, it was actually a mathematician named John Bernoulli who discovered it. In a letter from John Bernoulli to L'Hopital, and it just happened to, I guess, take on his name. But it actually turns out that this property, or this little rule we're going to follow here, was actually developed by a mathematician named John Bernoulli, who you'll definitely run into if you study higher levels of math. But ultimately, we're still just going to call it L'Hopital's rule. So there's a few things that need to go on so that you can use L'Hopital's rule. The first thing that absolutely has to happen is you have to have an indeterminate form, which of course means you should figure out if your limit gives you a 0 over 0 or some sort of infinity over infinity version, whether it's plus or minus. Second step is, of course, to do what the formula says. Take the derivative of the numerator separate from the derivative of the denominator, and again, we're not talking about a quotient rule here. The last thing is to take the limit of that new quotient. So let's go ahead and try L'Hopital's rule. We just did this problem right here on the last slide at the bottom. We know the answer is 12, but I'm going to put a big old X through that because that's the old way. Anytime now that you're taking a limit and L'Hopital can be used, I would absolutely use L'Hopital's rule. It usually will produce a much quicker answer, and in a lot of cases you actually won't even have a choice but to use L'Hopital's rule. So let's go ahead and use L'Hopital's rule. We again already know that the value of this limit is 0 over 0, which of course means we can apply L'Hopital's rule because we have an indeterminate form. All L'Hopital's rule says is we take the derivative of the top function separate from the derivative of the bottom function. So of course that's nice and straightforward here. The derivative of that top function is 4x, the derivative of the bottom function is 1, and then in that third step, like it says, we just need to take the limit of that new quotient. So of course plug in that value of 3, and 4 times 3 is that same value you saw from before, but took not a lot more steps, but definitely a few more steps, so we still get the same answer. So hopefully this L'Hopital's rule is something anytime you can use from here on out, you'll definitely take advantage of. Okay, the rest of these slides are really going to be devoted to a bunch of examples that need to have L'Hopital's rule applied to them. Some of them are going to be basic, some of them will be a little more complicated in terms of those AP kind of questions. But let's start off with some basic applications of L'Hopital's rule. So again, remember the key to using L'Hopital's rule is you have to have an indeterminate form. And just like you would have hopefully done back in chapter 1, the very first thing you should do is plug in the value that your limit is approaching. Here it's -2, and skipping over that arithmetic, you can just see that it'll be 0 over 0, which is in an indeterminate form. So of course we can apply L'Hopital's rule, which says take the derivative of the top separate from the derivative of the bottom, and then we can take the limit again. And here it's nice and basic and straightforward. The derivative of the top is 2x plus 3. The derivative of the bottom is 2x plus 1. Don't forget to put your limit notation, because now in this next step we need to take the limit again. So now we can take that -2, apply it again, and when we plug in that -2, we'll end up with -1 over -3, or simply 1/3. So you can see problems that are done with L'Hopital's rule can be much quicker, I think can usually produce less mistakes than had you tried to do this problem the chapter 1 way, so to speak, and do the whole factoring and canceling and all of that. But maybe there's going to be other problems where we're going to have no choice but to use L'Hopital's rule, and those would be the ones we'll really want to focus on. Here in this problem, we want to find the limit of sine x over x as x approaches 0. Again, we have to first determine if we have an indeterminate form. When we plug in 0, sine of 0 is 0, over 0 produces our indeterminate form. So we can of course apply L'Hopital's rule. One little note to make here, especially when you guys are writing out your answers to these types of problems, or the steps for these problems, is make some sort of indication that you're about to apply L'Hopital's rule, instead of just writing a bunch of limits that may or may not be connected to each other. It's a good idea to kind of separate these kind of steps of these problems, so that when we write this new limit, we know you applied L'Hopital's rule. The reason sine became cosine is because we took the derivative of it. The reason x became 1 is because we took the derivative of that. And again, we need that limit notation because now we need to take the limit of this new fraction after we apply L'Hopital's rule. When we plug in 0 for x, cosine of x, or cosine of 0 will be 1, divided by 1 is just the value of 1. So definitely nice and straightforward and very easy. Here in this limit, again, we need to verify that we have an indeterminate form, so we'll plug in 0. Cosine of 0 is 1, so in the top of our fraction we'll end up with 0. In the bottom, of course, it's just a 0, and that gives us the important form that we need so that we can use L'Hopital's rule. I'm going to go ahead and make the indication that I'm going to apply L'Hopital's rule here. So now let's go ahead and apply L'Hopital's rule. The derivative of the top of our fraction is negative sine x, and the derivative of the bottom is just simply a 1. Again, don't forget about the limit notation, and now we can take the limit again. When we take the limit again and plug in 0, we'll end up with a value of 0. So 3 definitely basic applications of L'Hopital's rule. When they're this easy, it's nice and fun because it's just straightforward. So what about different kinds of problems? Well, you can see right away here we're jumping up in difficulty in terms of the way this looks. Here we're trying to take the limit of a fraction again, but in the top of this fraction we have an integral where the top bound is an x. Luckily, the process still hasn't changed. Kind of think about what I said in every one of these problems so far. The first thing we need to do is plug in that bound, or that limit we're approaching, and in this case it's a 1. And since x is approaching 1, we're going to plug in 1 wherever we see an x. Since we see an x in the top bound of this integral, of course that's just going to produce the integral from 1 to 1. So in the bottom, it's nice and easy to see we're going to end up with a 0, but what are we going to end up with in the top? Well, remember something we saw way back from chapter chapter 4.3, I believe to be specific. Anytime you integrate from one bound to the same bound, and if you're associating that to area, this function doesn't matter. It could be the worst looking function in the world. It wouldn't matter what that function is, because remember, a definite integral has the concept of area attached to it. And of course, if we integrate or find the area from one number to that same number, there is no area. So luckily, that's just a value of 0, and in the bottom we have 0. So that produces an indeterminate form, which again means we can apply L'Hopital's rule. So I'm going to go ahead and make a little indication that we're about to use L'Hopital's rule. So of course the bottom derivative is nice and simple. Don't need to say much about that. So how do we take the derivative of the top of this fraction? Well, what you're going to have to recall back from section 4.4 is anytime you're trying to take the derivative of an integral where the upper bound has a variable in it, we need to use what is called the second fundamental theorem of calculus. And because of that, hopefully remember, it's just two basic steps. The two basic steps are this. All we need to do is take this upper bound and plug it into the variable inside of our integral, which would of course be the t. So we're just going to end up with e to the x squared. But what you can't forget to do, and I didn't write it in here, so it's up to you if you want to write it, we also have to multiply by the derivative of that upper bound, which is just x, or in other words, a 1. So that 1 wasn't of course required, doesn't really change anything, but if you need to see that we were multiplying by the derivative of that upper bound, then you might want to put that times 1 right there. Bottom line is, after that, it's nice and simple. Now that we've applied L'Hopital's rule and taken the derivative of the top and the bottom, we can retake the limit. And you'll notice, when we plug in 1, we'll get e to the first power, or just e, and when we plug in 1 in the bottom, we'll get a value of 2, so this limit is equal to e over 2. So, a much different problem than these basic ones we saw on the left, but still just an application of this idea of L'Hopital's rule. Another type of common AP kind of question you might run into, and we've seen this many times in terms of other problems, is what if they don't give you a function? They give us a bottom function, but they don't give us the top function. They just call it the function f. Luckily, nothing's changed. The very first step you're going to want to do is take that limit. Apply that limit you're approaching and see what happens. Maybe it won't be an indeterminate form. So we're going to end up with f of 2 over 2 minus 2 to the second power. Of course, in the bottom, we'll get a 0, and f of 2, if you look it up here in this table, is equal to 0. So we indeed end up with an indeterminate form of 0 over 0. Again, I'm going to make a little indication that I'm going to apply L'Hopital's rule, so let's go ahead and apply L'Hopital's rule. Don't overthink these things when they come across you. We're trying to find the derivative of a function called f, but we don't know what that function is. That's okay. The way we write that is just as f prime of x. The derivative of f is just f prime of x. In the bottom, we have a little application of the chain rule here, so be careful. We're going to bring the power of 2 down. We're going to leave the inside function alone, the stuff, because this is stuff to a power. We're going to leave that alone. We're going to reduce the power by 1, which I never animated in. And then, of course, we need to multiply by the derivative of that stuff. And luckily, the derivative of x minus 2 is just 1. So I wrote in that extra bit of info so you can remind yourself about the chain rule, but of course, we don't have to write that in. After we apply L'Hopital's rule, we're free to take the limit again. We're going to plug in 2 wherever we see x, so we'll end up with f prime of 2 over 2 times 2 minus 2. Of course, in the bottom, we're ending up with a 0, and then you can see from the table above, f prime of 2 is equal to 0, which means we get another indeterminate form. So you might have been asking yourself or thinking, is it possible to actually do L'Hopital's rule more than once in a problem? And you can see right here the answer would be yes. We have to keep applying L'Hopital's rule till we successfully find our limit. And since we got another indeterminate form, we need to again make the indication that we're applying L'Hopital's rule. So when we apply L'Hopital's rule here again, we're going to take the derivative of f prime, which is f double prime. The derivative of the bottom is nice and simple, that's just 2. And now we can apply the limit again, hopefully for the last time. If we take that value of 2, which we're approaching, and plug it into our fraction, we'll end up with f double prime of 2 over 2, and hopefully we won't be getting a 0 over 0, of course, here, because it turns out f double prime of 2 is 5 from the table above. So now we can finalize this answer and say that the final limit that we have here is the fraction 5 over 2. Okay, continuing on with a few more examples involving L'Hopital's rule, but make a note, these limits now are going to infinity. So in this first one, we can go ahead and apply L'Hopital's rule. The derivative of 15 is 0, the derivative of x squared plus 1 is just 2x, and we can apply L'Hopital's rule again. If we take the derivative of 0, it's still 0, the derivative of 2x is just 2, so of course 0 divided by 2 is 0. I hope you were kind of writing these things in a little hesitantly as I was talking through them. None of that actually should be there, and I'm going to just put a giant dislike button there because that's not the way we should have done this problem. I neglected to do something I said at the very beginning of all the problems, and certainly what you should always do when you are trying one of these problems. L'Hopital's rule only applies when we have an indeterminate form, and as it turns out, we don't have an indeterminate form here. This is actually a limit we know how to take. If you imagine plugging in infinity into the bottom of our fraction for the x, we'd have infinity squared plus 1, which is infinity. So 15 divided by infinity, or 15 divided by the idea of growing, or of a number growing without bound, would of course just be 0. So as it turns out, sometimes you can get answers by luck, but of course your process and how you got there is really what matters the most. So be careful, don't kind of get wrapped up in always doing L'Hopital's rule. Sometimes you don't need to do L'Hopital's rule, and this would be a good example of that lesson. Hopefully you won't have to learn the hard way in case you ever run into one like that. So let's, instead of doing a trick one like that, let's go ahead and definitely do one that definitely needs L'Hopital's rule. If we take this limit, we'll have to for sure see some sort of indeterminate form so we can use L'Hopital's rule. In the top, we'll have infinity squared. In the bottom, we'll have e to the positive infinity. And take note, we're going to negative infinity as our limit. So of course, that negative in the top of the power would make that a positive infinity. So what is the limit as e goes to infinity? Well, keep this in mind. You've had this little graph and these limits in your notes now for a while since chapter 5, but I think it's really important to revisit these because we're going to see them a lot more often again now. Two very basic limits you're going to have to know, and here are the graphs to kind of prove that. If you ever have e to the x going to positive infinity, you'll notice that that graph is going towards infinity. If you ever have e to the x going to negative infinity, you'll of course see that that graph is going to 0 since our x-axis is serving as an asymptote. So just kind of keep those limits in mind because we're still going to need them throughout this chapter and actually into chapter 9 as well. Okay, so back to the problem at hand. We end up with infinity over infinity. That is most certainly an indeterminate form, so we need to apply L'Hopital's rule. In the top of this fraction, not too bad. Derivative is 2x, but be careful. In the bottom of this fraction, the derivative of an exponential function, e, is itself. So we have e to the negative x. But since that power wasn't a plain x, we need to multiply by the derivative of that power, which is of course negative 1, or we'll just write that as negative e to the negative x. After we apply L'Hopital's rule, we again are free to take the limit. And in this case, we're going to negative infinity, so we'll end up with negative infinity in the top, negative infinity in the bottom. That is still an indeterminate form, so we need to apply L'Hopital's rule yet again. When we take the derivative of the top, we'll end up with 2, and when we take the derivative of the bottom, we'll have to multiply by another -1 because of the chain rule application. So those two negatives would of course just become a positive e to the negative x. When we take this limit, we'll end up with 2 over infinity, and just like you've kind of seen before, a number divided by infinity or a number divided by the idea of a number growing without bound is just equal to 0. So that'll be the final answer. One more here of a limit going to infinity. So we have to verify if we indeed have an indeterminate form, and again, this is fairly simple to see. The top will definitely be infinity, the bottom will definitely be infinity, so we can go ahead and apply L'Hopital's rule to see if we can get this limit to work out. In the top, fairly straightforward derivative, of course, that's just 2x. Be very careful in the bottom. We actually took this derivative in our notes way back in chapter 5, but that is going to require, and I'm just going to abbreviate this as product rule. It's a function x times another function ln x, so we need to apply the product rule, which you can see here. I'm going to go ahead and clean this up a little bit before we retake the limit. X times 1 over x is just 1, of course, and now we can retake the limit. But again, we're going to end up with an indeterminate form. 2 times infinity is infinity. 1 plus ln of infinity, by the way, ln infinity is infinity. That's just another infinity, which again now means we need to apply L'Hopital's rule. In the top, again, a very basic derivative. In the bottom, another basic derivative, but just be careful. The derivative of ln x is 1 over x. And unless you want to take a limit with this fraction inside of a fraction, I would recommend doing a little copy change flip or copy dot flip, depending on how you were taught it. Basically, we're going to take that fraction in the bottom and flip it. Ultimately, that gives us 2 times x over 1, which is really just 2x. And now you can see we have a nice, easy limit to take. We're going to plug in infinity, and of course 2 times infinity is just infinity. Okay, in these last two sides, what we're going to do is attempt to just address the last two types of indeterminate forms that you really need to be worried about. There's actually several indeterminate forms other than the 0 over 0 and infinity over infinity, but in these last two slides, we're going to look at 2 other ones just to kind of get a complete picture somewhat of L'Hopital's rule. So just as a quick little overview, there are actually, and I'm kind of making up this word, but there's several determinate forms where you don't need L'Hopital's rule. If you ever take a limit and get infinity and plus infinity, that's just infinity. If you ever get a limit where you get negative infinity minus infinity, well, that's just negative infinity. If you ever get a limit where you have 0 to infinity, that's 0. And if you ever get a limit where it's 0 to negative infinity, that's infinity. We won't go over the particular reasons why these are true, but these are what I would call determinate forms. In other words, we know the answers to them without having to do this L'Hopital's rule. But I really wouldn't anticipate on seeing any of these. So then what about some sort of other type of indeterminate form? Well, what we're going to do here, as you can see at the top of this slide, is take a look at an indeterminate form of 0 times infinity. And other than what you might believe that might be, which some people might believe is infinity or 0, it's actually neither of those. It's an indeterminate form, so we need to do more work. So let's take a look at a couple problems that might involve that. So what if we try to take this limit right here? Well, if you think about it, if we plug in infinity, e to the negative infinity would be 0, if you refer to that last slide. ln of infinity would be infinity. And now we have this special other indeterminate form. It's not one of these 2 types that we got used to seeing, but it's still an indeterminate form, which means we need to do more work to get this to work out. The more work we're going to do in a problem like this, and it's not obvious, but if you think back to all the problems we've done so far in this section, they've always been fractions. And you'll notice we actually do have a fraction here, but it's not written that way. We can think of that 0 as being 1 over infinity. The reason I know that 0, or can be thought of as a 1 over infinity, is we can send that negative power on the x for the exponential function down to the bottom of a fraction, which would then give us the indeterminate form of infinity over infinity. And that is definitely good because we can use L'Hopital's rule to make this one work out. So just be careful. This 0 again is being viewed as 1 over infinity. It's really not 1 over infinity, of course, but it could be thought of it that way because of that negative power on the e. So if we set that to the bottom, we would end up with a regular, so to speak, indeterminate form. And now we can do what we've seen in all these other slides. We can apply L'Hopital's rule. The derivative of ln x is 1 over x. The derivative of e to the x is e to the x. I'm not going to take this limit yet until I simplify it a little bit. So I'm going to go ahead and send that 1 over x to the x in the bottom of that top fraction to the bottom of the overall fraction. So we're going to end up with 1 over x times e to the x, and of course if we plug in infinity, we'll have infinity times infinity, or just infinity, and of course 1 over infinity is 0. So that's one other way to kind of look at these indeterminate forms. Let's take a look at this one, a little bit different. Here we're taking the limit as x goes to 0 of x cotan x. So what's that going to be equal to? Well, we know that the limit as x goes to 0, we plug in 0 for x, so that's just a 0. But when we plug in 0 for cotan x, that's equal to infinity. And the best way to see why that's equal to infinity is cotan is really cosine x over sine x. And of course, if we plug in 0 into that, cosine of 0 is 1. Sine of 0 is 0. And of course, 1 over 0 is what we kind of view as the idea of infinity. We can't divide by 0, so that's kind of that idea there. So because of those things, how are we going to approach this problem? Well, instead of writing it as cotan x, we can think of that infinity we're getting as 1 over 0, like you can see above here. And because of that, we just need to alter cotangent just a little bit to make this work out. So we need to write this as a fraction. So instead of writing it as cotan x, we can write that as 1 over tangent x. If you recall back to your reciprocal trig functions, 1 over tan x is cotangent x. And because of that, now we can actually apply L'Hopital's rule. If we plug in 0, we'll get 0 over tan 0, which is 0, and that's our indeterminate form. After that, of course, we can apply L'Hopital's rule. The derivative of x is 1, and this one we don't see too often, so be sure you kind of are at least aware of it. You don't necessarily have to have it memorized. The derivative of tan is secant squared. So let's go ahead and plug in our limit. But here, maybe you're not so well versed necessarily with secant of 0, so maybe it's better if we view secant as 1 over cosine. And of course, if we view it as 1 over cosine, we can just kind of flip that to the top, and it really just is cosine squared. You really didn't have to do these two steps right here. It's not necessary to do these two steps, but if you weren't really too sure what secant of 0 is, I certainly hope you would know what cosine of 0 is, then maybe these two steps here I circled would be pretty important in terms of you kind of figuring out this problem. But either way, now that we know we're just really taking the limit of cosine squared, we'll plug in 0. Cosine of 0 is 1, so of course 1 squared is just 1. Okay, one last special indeterminate form that we're going to address here that L'Hopital's rule will help us out with is this one up here. Infinity minus infinity. Despite what you might want to believe about what that could be equal to, it's definitely not equal to 0. It's just a meaningless mathematical statement, so we need some sort of other techniques when we run into that indeterminate form. So let's see, do we have that indeterminate form here? Well, if we plug in 0 here, we'll end up with 1 over 0, which we view to be the value of infinity. And in the bottom, it would be the same thing. e to the 0 would be 1. 1 minus 1 is 0. So we'll end up with another 1 over 0, which again we view to be infinity. Unfortunately, infinity minus infinity isn't 0, so we can't use L'Hopital's rule yet. L'Hopital's rule only applies when we see these two indeterminate forms. And I think if you kind of took anything away from that last slide, we're just trying to get our problem to be one single fraction, because that's when we can use L'Hopital's rule. So that's going to be the goal here. I'm going to do all of this off to the side. We need to make our problem one fraction. And to make that work, we just need to get a common denominator. The common denominator would be x times e to the x minus 1. So in this first fraction, we're missing the e to the x minus 1. So I'm going to have to put it in the bottom and also in the top. This second fraction is missing the x of the common denominator. So again, we'll put it in the bottom, but we also have to put it in the top of that fraction. Once we have that common denominator, we can add these two fractions together. We'll have e to the x minus 1, which is right here and right here. And then, of course, this minus x is the one that we see right here. So now we have this one big fraction that now we can attempt to apply L'Hopital's rule to. But we got to first check, is it even appropriate to use L'Hopital's rule? Well, let's see. If we plug in 0, e to the 0 is 1. 1 minus 1 is 0. Minus another 0 is 0. And in the bottom, of course, we'll have another e to the 0, which is 1. 1 minus 1 is 0. So yes, we do definitely end up with an indeterminate form of 0 over 0, which means we can apply L'Hopital's rule. Now, be careful here. The top of this fraction is a pretty easy derivative to take. E to the x becomes e to the x. This minus 1 goes away. The derivative would be 0. And then, of course, the derivative of minus x is minus 1. So how do we take the derivative of this bottom part? Well, I'm going to kind of skip over all those details since we've seen product rule many times before, but just take note that the derivative here would require a product rule. Assuming all goes well, you'll end up with that product rule result in the bottom of the fraction, and now we're free to again take the limit. And you'll notice we'll end up with another 0 over 0. In the top, e to the 0 is 1, 1 minus 1 is 0, and in the bottom we'll still have that same result of 0, and that's not a big deal. We've already seen a few of these problems where it's okay to use L'Hopital's rule more than once. So let's yet again apply L'Hopital's rule. In the top of this fraction, the derivative is again nice and simple. It's e to the x minus 1, but again, be careful here. This piece of the bottom of this fraction, just that piece, is going to be a product rule. E to the x is luckily just e to the x, and then this minus 1 becomes 0. The derivative of a constant is, of course, 0. So the first piece needs a product rule again. The derivative of e to the x is just e to the x, and then minus 1 just goes away and becomes 0. So now we've applied L'Hopital's rule again, so we're free to plug in 0 again to take this limit. And maybe this time we won't end up with one of our indeterminate forms. We'll have an e to the 0 in the top, which is 1. This little piece right here, of course, since we're multiplying by 0, goes away. That just becomes 0. And then we have 2 e to the 0's in the bottom. So these e to the 0's are all 1, so we'll have a 1 in the top, a 1 plus 1 in the bottom, or an overall answer here of 1/2 for this limit.